Um, Hello, everyone. My name is Ye. I'm the co-founder of Scroll. So Scroll is a general purpose scaling solution for Ethereum. So basically, you can think of it, if you are a developer, it's the same as Ethereum, but cheaper, faster, with a higher throughput, and secured by zkEVM. And today, I'd like to introduce one experiment we are working on. So it's not like we are committed to this approach, but our research team is working on some solution in parallel to have a really fast zkEVM or zkEVM, and eventually apply to many circuits designed through the zk protocol called GKR Protocol. So let's start with some intuition. So this is like in the past, like how zk is being used. So if you want to prove some program, and for example, program A is written in some high-level language, you have to handwritten a circuit, which include this kind of addition and multiplication gates. And then you generate proof. And for different program, you need to write different circuits, and which is very kind of hard to write because you require kind of Solidity developer or high-level language programming developer to write a very low-level like circuit. And for different program, different circuits and different proofs. And then different teams are start working on zk virtual machine or zkEVM to make things simpler. So the idea is that you don't need to write any circuit. You only need to have one universal zk virtual machine circuit or zkEVM circuit to prove any program you have. So you take program as a circuit input, and then we build a very complicated virtual machine circuit to prove that the program executes well on the virtual machine. And then you get one universal proof to prove for arbitrary program. So this is the idea behind zk virtual machine. And if you look at the design for zk virtual machine, so there is a program and there's the input. And for different program or different input, you will have a different execution trace. And for example, for program P and X, the execution trace will look like push, pop, add, more. It's a sequence of opcodes you are executing. And then with a different input or program, you get a totally different execution trace. So this is very similar to running a program on CPU, which you get a sequence of assembly code. And now within this kind of virtual machine circuit, you need to prove that this trace is valid, it's consistent, or the kind of push and pop are consistent within the same stack operation. So the idea is that you can build some universal circuit. In each slot, it's it's a metaphor called a opcode processor, which can process the logic of different opcodes. For example, the same opcode processor can process either push, pop, or any opcodes you fit into that slot. And then this opcode processor, it's more like a if-else logic. If its input is push, it can prove push, and if it's other opcodes, it can prove other opcodes. So it's a very general logic to prove anything. If you zoom into what the opcode processor look like, the layout, so there is control logic, which we're controlling which opcode is actually proving, and also the data proving that you are fetching from the rest stack, rest memory, rest storage. So basically, it proves that this opcode is correct and it's consistent with the memory stack, and it's selected by this control logic. But here is a problem, because as mentioned, because every time execution trace is different, so which means your opcode processor need to contain a very complicated control logic to select which opcode you're actually proving. So there will be actual overhead in each step because you need to kind of be compatible with all the possibilities for different opcodes. And second thing is that to make this zkEVM circuit become universal, so one thing you need to do is that you need to have a fixed upper bound to pad your whole circuit. For example, your circuit size will be 220, then you can only prove a limited number of opcodes. So because your circuit needs to be fixed, which means even if you are proving some program with fewer opcodes, you still need to pad to the maximum length. So that's in the past. And now, the intuition is that, okay, so we want to reduce the overhead of this zk virtual machine. And one idea is that instead of proving a generic logic for each slot as a trace, you prove what you need. So for example, this is your execution trace. You have push, pop, add, and more. And then your circuit, you just construct a different circuit to prove, for example, you have push circuit. It's a imagine push circuit is very small, and then you put push there, pop, add, and more there. So you basically only prove for what you need. And every time a different execution trace will result in a different like circuit because you have different like sequence. And now like, there is a big problem for this because now your verification change every time because the verifier don't know like, what's happening in your virtual machine circuit because the circuit is related to what your trace look like. And so that's a problem. Your verification change every time. And the verifier need to know the circuit ahead of time. But for zk virtual machine circuit, verifier is like universal. It doesn't need to worry about anything. So we want to combine the best practice from both sides. We still want to have one proof for any circuits, but also we want to reduce the overhead on the prover side. So the intuition is that you have different programs and different inputs, and then on the fly you generate different circuits. And then like use a different prover to prove that. We call that a non-uniform prover. So the non-uniform prover means like the circuit you are proving is different every time. So it's not a uniform one. And then like different program and different input would have different proofs and according to different circuit. And then to get that become universal, you get a uniform verifier to kind of translate this proof into a universal proof. So like one way to look at this is that a zk virtual machine circuit or zkEVM circuit can handle this kind of non-determinism from the program on the first layer, like from the prover layer. So you build a virtual machine circuit to handle the non-determinism from the program and the input because you are handling different traces using the same circuit. But now like you are kind of move this non-determinism to the verifier side. So one like very, very simple way to construct this solution is that you get different circuits every time on the non-uniform prover side in the first layer, and then in the second layer you just use a zk virtual machine, a smaller zk virtual machine to handle different proofs. So that's how you kind of can make this become a universal proof, like in the end. So there's the pros and the cons. Like pros is that the prover can be extremely fast. So that's the purpose of this experiment because we want to see like how fast the prover can be, because there's no overhead at each step. You are proving what you need, and you can prove that dynamically. And also, second thing is that we find there's a lot of like program optimizations you can do to make that even faster. For example, like if this program has a lot of for loop, and there are some special way to make this program like prover even faster. So you can do a lot of like per program optimizations on the prover side. So this is the pros. But the cons is that verifier, again, like the uniform verifier has a larger overhead because the verifier need to know the circuit, and there is a cost paying for this uniform cost, and that will still be huge. So the intuition is that because verifier, like after one layer prover, verifier can already reduce the complexity from n to log n. So that's why the intuition is that the uniform verifier, like aggregation overhead, will be smaller, but in practice it might still be very large. So that's two problems. And then like we again like the reason become like why we are considering like experimenting this using the GKR protocol, and what's the rationale behind. So to start, to give you some context about like what is GKR protocol. So this is a high level like introduction of how it looks like. So imagine like you have a program and you have an input, and you need to prove that this input like after executing on this program get this output. And so you start with your public input, and so GKR is require a layered circuit. So this is a first layer, and there are addition gate, there's a multiplication gate, and there are input propagate from the input layer to the first layer. And then it propagates to a second layer, which is also a layer of addition and multiplication gate. And then like it propagates layer by layer, and then till the end you get the output. So what you want to claim is that the prover knows some public input that after executing on this kind of layer circuit, you get the claimed output. And this is quite different from like, not that quite different, but it's in some sense different from RNCS and Plonkish, where you have a table and you just need to write the constraints. So this is actually more like closer to like how a circuit, how a program really look like, how this kind of variable flow from the first layer to a second layer to a third layer. And like how to prove this? So in every layer, because there is addition and multiplication, so there is input variables. So in each layer, there will be a multivariate polynomial interpreted from the variables in that layer. So for example, there is a D layer, and then you get a multivariate polynomial interpreted from the input layer. So you get a multivariate polynomial there. And then for every layer, you will get a multivariate polynomial, like from 0th layer to the dth layer. So this is like only like talking about like, this is very similar to like in a Plonky circuit, you get every column, and then you interpret each column into a like univariate polynomial. But here, it's every layer will interpret into some like multivariate polynomial. And then like you get all the witnesses, and the circuit will be, so the logic is that after one layer, the value propagates to a second like layer of value. So the circuit logic is basically a transition function defined between different layers. So like how you move, like so VD is the value of the dth layer, and the VD minus 1 is a value of D minus 1 layer. And then the circuit logic is defining how you transition from VD to VD minus 1. So this is your circuit. It will encode like addition or multiplication. So this is like, the bracket contains the circuit logic, and you need to prove this logic over those two polynomials. And then like what the prover need to do is that firstly, prover need to commit to the public input, and it will get some commitment to the input layer. So this is the only like thing you need to commit to from the prover side. So it's a commitment to the input layer. And then like the prover need to run a bunch of sum check protocol, like between two adjacent layers, and it will broadcast in a reverse way, because you start from a public output, and you want to prove that this public output is correct, is valid, and then like it's because it's propagated from the previous layer. So you need to prove that if public input is valid, then like there are some value. So this should be the evaluation of the polynomial in the previous layer. So you basically like deduce from the public output to the previous layer, and then to the previous layer until the end, where there are some arguments like, if this is a public output, this should be the opening for the public input polynomials. And sum check is a very, very efficient protocol to prove that, like if you brute force on hypercube that, so it's basically like you have a polynomial and you brute force all the values within a field, and it adds to some value. So we use sum check to prove like the relationship between two different layers. And sum check is super efficient because prover only do linear time operation, and also it's field operation, not the group operation. And then like, from this deduction, from public output, you go to the final output. And then like prover only need to do one opening on the public input polynomial and prove that this commitment is related to this opening. And the prover overhead will be linear to a circuit size. So here D is the number of layers, which is basically the depth of the circuit. And N is how many variables you have like in each layer. And then like prover also need to do a multivariable opening. So this is why it's very flexible, because it can also plug in any polynomial commitment scheme. For example, you can use a multivariate version for KZG, a multivariate version for Fry, or any like linear code in like error code based like PCS as Fry. You can change that to multivariable session. And then verifier will be very efficient because it's only like log n to the so n is the width of the circuit and its log size, and the D is the depth of the circuit. So we are trying to minimize the depth of the circuit in GKR setup. And there's a T. So this T is very, very bothering. So this is actually one important reason why GKR hadn't really been like carefully considered in the past. One reason definitely comes from like it's very hard to write a layer circuit. Second reason is that the verification overhead is usually very, very large for a general circuit, because T, if you didn't write your layer circuit very carefully, it's not structured. The T can be like linear to like how many kind of evaluations you do for those multivariate polynomials, which is related to the general circuit size. So this is why like verifier can be very, very bad for GKR provers. And then you also need to open you need to prove this kind of multi-open polynomials in the end. And now like why we choose, like we are experimenting GKR on zkEVM. So the reason that firstly, you don't need to commit to the whole witness. As I mentioned, like the only thing you need to commit to is the input layer. So because the values are propagated from the input layer to a second layer to a third layer. So as far as it's connected, it's computed from the previous layer. You don't need to commit to that. But in all the kind of RNCS or like Plonkish, you basically need to commit the whole thing. So this is why like you can massively reduce the number of elements you need to commit to. So that's the first advantage. And second advantage is that because the core protocol, like the core behind this kind of GKR protocol is that in every layer you run a sum check protocol. And sum check protocol is orthogonal to the choice of field. So basically you can do, so this is sum check protocol, you can choose any field you want. Even for like, because it doesn't require FFT, the field doesn't even need to be like FFT friendly. So you can choose arbitrary field you want for this kind of sum check protocol. So this is why another reason why it might become very, very efficient, because you can choose any field. Because one observation we find from previous experimenting on our zkEVM is that larger field will always be, because like sometimes people compare like larger field with smaller field because larger field might require recursive operation, all those stuff. But another biggest cost from larger field operation is that you also need to compute your witness and your whole circuit carrying this large field. So that's why like witness computation and every step will become slightly more costly than smaller field. So that's why like it's still very important to make this as a consideration. I think the third thing will be like the verification is definitely very bad for a general circuit, but the verification is actually way smaller for data parallel circuit. So imagine the gray area are like identical circuit, and it's the same logic. And then like the verifier, the T is only like related to the very, very small sub-circuit size. So in zkEVM, we have many, many repeated operations. So that's why it makes verification become smaller. So that's why it become a consideration, because verification is actually smaller in this case. And the first thing is that there are some efficient lookup arguments, because one fundamental thing for all the GKR protocol is that you need some lookup to kind of do the RAM operation. You need to delegate to stack, to chips, and then like efficiently read the elements from there. And there are some efficient lookup arguments called logup, which is a GKR-based MA lookup table. And the idea is that if you are familiar with MA lookup or this line of work, so the biggest improvement from previous plookup is that it changed this kind of product, this accumulation, to some addition of some fractions. And then so this is the equation. If you can prove this equation, you can prove that there is lookup relationship. And the way you do that in a GKR-based system or a layer circuit is that, so imagine you are adding A0 divided by B0 plus A1 divided by B1. And so those two pairs will become your circuit input. And then the GKR circuit, the repeated components will keep computing this computation. And then it's a tree structure circuit to prove this kind of addition for friction very efficiently. And then because it's also data parallel, so that's why you can make that very, very efficient. So basically, it can also handle this kind of lookup very efficiently with this backend. And now final thing come to the design, how zk virtual machine or zkEVM can look like with this backend. So let's start with some very, very basic design. So you have different execution trees, and then you put all the same opcode at one. I put that at one column, but as I mentioned, you actually lay out that in a row because it's logged to the width of the circuit, and so you don't want to add the depth of the circuit. So basically, you put all the opcodes together and in the same column, and then all those opcodes will link to stack, memory, or other chips, which is some other circuits like Ketchak or those more unfriendly circuits using lookup tables. And so this is a basic design. So basically, opcode will become dynamic. So if you have 5 opcodes, 5 push, it will only contain 5 push. And then as I mentioned, for each of those columns, you will use this structure, this data parallel circuit to handle from input to output. So it's layered in a row, where it's push, push, push. It's the same structure. And then for this lookup table, you can use tree structure circuit to prove that. And another optimization, like we have done, like in the we observe is that this can be very efficient for some kind of, if your program is massively like rely on some for loop. So this is why I mentioned like this is not just for like EVM, VM. It can be easily generalized to any kind of zk machine learning program or like any program with large repeated for loops. Because imagine like this is your layout of your program, and you have a program like a block diagram like this. So you start from input to the first block, to a second block, to a third block. So we have some kind of nice findings about like if B2 block is repeated multiple times, you can make that become like one of the basic components of the data parallel circuit, your GKR circuit, and then you can save all the stack operations within that circuit. And the high level reason is that because within one block, you only, so the elements you read and write are consistent with each other. So you can handle that within this kind of layered circuit. So there are some very complex details, so which I won't go into very deeply. But basically, if you have for loops, you have very complete for loop, like this might be a very good choice for you. So this is a layout for a basics block where those are like opcodes. So you have input containing your program counter and stack operation and your input, and then those are like two different opcodes. And I'm drawing a figure for a block which contains several opcodes, and they are connected with each other. And then like you basically lay out all the blocks also in the same row and then like use one GKR protocol to prove that very efficiently. Yeah, I think that's mostly like, for the construction, a high level intuition for the construction. And I want to mention that there are so many challenges, but we are still very optimistic about the future. So one thing that I didn't make the slides, but I want to quickly mention some of the unsolved problems here. So we are talking about this, but it doesn't mean like we are really committed to, we have to change to this, because it's a still very early stage experimentation period, because there are still a lot of unsolved problems. One thing, as I mentioned, is that how large is the aggregation cost, and like whether there are some polynomial commit scheme, which like it had a very small overhead on the aggregation side for this multivariable like derivative. So that's one thing, the verification overhead still needs to be figured out. And second thing is that, which I think a lot of projects, why like people are like keep using RMSA and Plonkish, is that because there are no good toolings and infrastructure or like front end for people to even try like what does the GKR circuit, the efficiency for that even look like, because it's very hard to write such layer format, because it's very easy for you to write gates, write like custom gates, but here every time you require different like multivariate like custom gate. So it's very hard to write the circuits, and also you need some efficient implementation. But the good thing is that we already see a lot of really promising results from different teams. Like I think Model Labs, Polyhydra, a lot of other teams are like building this GKR based proof system, and then like it's already proven that it can be like order of magnitude even faster than like the same Plonky circuit running on CPU. So there are still a lot of unsolved problems. So we still need more benchmarks. So there are research group working purely on research, working on this direction. But we do believe that like with some technology, with the kind of proving technology keep improving, we can make the zkEVM become like 10 times, 100 times faster, and eventually we will see like maybe 10-second zkEVM prover, and which is like within one block time, which can fundamentally change a lot of things. Like for example, like even how ECM work, because ECM the builder can generate a proof for the block he's building like within a block time, which it will change a lot of things. Like even change like maybe even for some infrastructure like PBS or light client, because you can do a lot of things. So you can remove some trust in relay, or you can remove like a lot of things like from the what currently we have. But we are also cautious that we won't make very aggressive move, because security is always the driving factor for us to make all the decisions grow. Because it's not only like the fastest prover will always be the best. We need to be very cautious about like how we move there with a product ready like release on mainnet. So this is still very early stage, and like looking forward to more collaboration. If different projects are interested in kind of collaborating on this topic, we already know a few projects want to explore this direction. So I think one thing is that we really want to kind of do the same thing as we do for the Halo 2 and zkEVM, where it starts with some community effort, it's fully open source, and like a lot of teams like us, PSE, as well as some other members are contributing to this jointly. And then later it becomes some really good standard, like different teams are building different gadgets, building different front ends for the circuits. So I think that will become really great because you have some community to back you up to do this experiment. And also like, because having this kind of shared stack will also enable like, the prover, like GPU prover, like a lot of teams might be more incentivized to work on like hardware acceleration for this backend. And so if any projects want to seriously like put some effort into this exploration, feel free to reach out to us. And we believe that there might be some interesting stuff happening there. But again, like this is a very kind of like exploration stage. So I think that's all for today. And thanks for listening.